working our way through all the motifs, or the dwarfs. And here we are at the fast Fourier transform and many of its relatives. I'm going to concentrate on the fast Fourier transform, but in particular, a lot of my data will be for the 3D Fourier transform, since that's what people use a lot of in practice. And so, just like the last few talks where I've talked about how to do these motifs, I start with a mathematical definition, make sure we understand that, work my way down through the parallel algorithm, and then give you a bunch of measurements at the end to kind of explain where the bottlenecks are and how people have tried to improve them and what the tuning space looks like. So I'll do that first for the one-dimensional FFT, but then a lot of the examples will be for the three-dimensional FFT, where you have a cube of data and you're doing the FFT in each direction. And that's a very common application. And then I will also at the end tell you a little bit about auto-tuning for FFTs, because Fourier transforms are among the most popular algorithm. If you've ever looked at a JPEG figure, you're using the FFT. That's how those are compressed, and to save memory without losing any of the quality of the picture. And so people are very concerned about making it run fast, and there are two particular very successful and widely used projects. In fact, if you've ever typed FFT in a programming system, you've probably used code that comes from one of these two auto-tuning projects. So I'll say a little bit about those two. They're still very active. They just had a release a month ago, for example, one of them. So let's go back to the FFT and do the definitions and make sure we understand how it works. So if I ever use the letter I as a subscript during this lecture, correct me, it's always going to be the square root of -1, just so we keep all that straight. And all of my matrices, just to keep the math easy, are going to be indexed from 0, not starting from 1. And so the discrete Fourier transform in one direction is a matrix vector multiply. There it is, F times V. And F is a very special matrix, and I've written down all its entries for you. The j-kth entry is this magic complex number to the j-kth power, where j and k run from 0 to m-1. And omega is a root of unity. So it's e to the power 2 pi square root of -1 over m, and there it is in terms of sines and cosines. It's a number on the unit circle, and when you take it to the mth power, you get 1. And so that is the matrix vector multiply that we want to do. But I don't want to do it in the obvious n squared time. I want to do it in n log n. Now that's the one-dimensional FFT. So what's the two-dimensional FFT? If I have a matrix, what I'm going to do is take each column, do the FFT, and then I'll take each row and do the FFT. And if I want to write that down in linear algebra terminology, when I pre-multiply my matrix V by F, that's doing the Fourier transform to each column independently. And when I multiply it on this side by F, that's doing it to the each row independently. And of course, matrix multiply is associative, so I can do it in any order I like. And higher dimensional FFTs are analogous. Maybe a little harder to write down in matrix multiply notation, we can, but it's the same idea. So I'm sure many people here have their own favorite applications of Fourier transforms, so signal processing being one of the most common ones. And I'll just do a one-slide example of that. Image processing, again, a one-slide example of that. But the running example I'm going to use to motivate it is the same one that we've had before when I said, why am I doing multigrid? Why am I doing all these other ones? It's going to be solving Poisson's equation. And this is one of the not quite optimal. It's going to be n log n instead of order n algorithm to solve Poisson's equation. But the constants are such that it's quite competitive with multigrid. And depending on your platform and the dimension and how many processors you have and all of that, this might win to solve Poisson's equation on a perfectly regular mesh, or a multigrid might win. Another example is this is a kernel of the fastest algorithm known to multiply very, very large integers. Okay, so let me do two simple examples. The first one is a one-dimensional FFT from signal processing. So here's an incredibly simple signal. It's a sum of two sine curves, a high frequency, 7, and a low frequency, 5. And I'm going to sample it at 128 points, and there it is, this nice smooth curve. And when I do the FFT of it, I'm going to get, of course, another vector, but it's going to be a complex vector. So let me just show you the real part and the imaginary part. The real part happens to be all 0, and the imaginary part only has a few non-zero components corresponding to the 7 and the 5. So what I've done is, the Fourier analysis of this signal, and I said, oh, you're the sum of two sine curves. And the height of these bars tell me that there's a 1.5 as the coefficients, and their locations tell me it's 7 and 5. So, but that's not what I really can measure. I measure something with a lot of noise in it. So here I've taken that same signal and I've added a random number at to each entry, which is somewhere between plus minus 3/4. Now and that looks very jaggy, and what I'd like to do is recover the original signal. And when I take the FFT, what do I get? Well, all those zeros stay quite small. I mean, those are very small little jags compared to that. And the same thing happens to this. The noise is spread out this way. And so what is the obvious way to try to recover the signal? Well, I'd like to recover that flat line from there. So all I'm going to do is take every number that's smaller than a certain threshold. I'll just pick a quarter and zero those out. And it almost all turns into zero except two little bumps there. And I'll do the same thing to the imaginary part, and almost everything goes away. And when I now do the inverse Fourier transform to go from here to there, I get almost exactly back what I started with. So that's the classical example of signal processing. So let me now do the same example, well, sort of in 2 dimensions. So here is an image we look at every day. It's actually built into MATLAB. And so here's how I'm going to compress it. You can just think of this as a matrix where every entry, has a red, blue, green kind of component in it. And I'm going to do the 2-dimensional FFT. So I'm going to pre-multiply. I'm going to do the FFT of each column and the FFT of each row. They don't have to be the same size. And then here's one way you could imagine compressing it. I'm just going to, as I did in this picture, I'm not going to store all those zeros. I'm going to throw away the zeros and just store the largest, in fact, 2.5% of the components. I'll throw away all the small ones, and I'll just keep the largest 2.5%. And so that's, I've just saved 97.5% of the storage for that image. What happens when I do the inverse FFT and look at it? I get this sort of clown back, okay? So it's sort of surprising that you can get a lot of detail just by saving that little data from the original image. Now, how does JPEG work? JPEG uses a similar idea, except what it does is it takes this image and it breaks it up into little 8x8 blocks of pixels, and it does a 2-dimensional FFT. It actually does something called the cosine transform. I'll tell you what that is, to each block. And then it says, now how do I compress that? What it does is it would take this image. It doesn't throw away the smallest entries. It just takes each entry and rounds it to a few bits. And that's how it saves all the storage. And then when you un-FFT it, you get back the images that we're all used to looking to. I mean, this is a JPEG image. So this is something that's used all the time. So those are 2 canonical examples. But the one that I'm going to mostly run with today is Poisson's equation, again, as usual. So just to remind you, if you need any reminding, because I've used this example so many times, there's the 3-dimensional version, which I will actually give you the data for the 3D FFT, how to make that run fast. There's the 2-dimensional equation. There's the 1-dimensional equation. And I will do the math for the 2-dimensional equation. And as we know, solving this comes up in all sorts of areas, not just gravity and electrostatics or heat, which I've used before, but all these other places as well. So let me just remind you of the notation for a couple of slides to write down the answer. How do I solve this with the FFT? So there's the 1-dimensional FFT. I need to solve a system of linear equations where the coefficient matrix, I'll call it L1 for 1-dimensional, L for Laplacian, 2's down to the diagonal, minus 1's off. Very familiar. There's the 2-dimensional one, which is just 4's down the diagonal, negative 1's for the derivative in the x direction, left and right, negative 1's for the derivative in the y direction. Looks like that. So now, on one slide, how am I going to solve this system of linear equations, L2 times x equals b? So I'm just going to remind you of 2 basic linear algebra facts. So the first fact, oops, you're back, okay, is that if I take that 1-dimensional FFT, 1-dimensional Laplacian, 2's down the diagonal, minus 1's off, I can explicitly write down its eigenvalue decomposition, and the FFT tells me everything I need to know about it. So this says that this matrix can be written as a matrix of eigenvectors times a diagonal matrix of eigenvalues times its inverse. And what is this matrix F? It's not exactly the FFT, it's just the imaginary part. And so all the ideas that I know about doing FFTs fast, I can just take the imaginary part. Works just as well. And so there's the explicit formula for them, just a bunch of signs at evenly spaced points. And there's another formula for all the eigenvalues. So that's the first fact. You can confirm it yourself and do the trig if you like. The second fact is I can write down the 2D Poisson equation in this slightly different way. So now x is not my vector of unknowns, it's my matrix of unknowns. So I'm just going to think of, I'm trying to solve it on Poisson's equation on a 2-dimensional grid, and so x are the values of the grid points. And L1 times x is applying the Laplacian to each column. That's the second derivative in the y direction. X times L1 is applying the Laplacian to every row of x independently. That's the second derivative in the x direction, so that's Laplace. Laplace is Poisson's equation. Second derivative with respect to y plus second derivative with respect to x equals the right-hand side. So I'm given L1, b, and I want to solve for x. So here's the 3-line algorithm. That's all I need to do. So let's suppose I just substitute this eigenvalue decomposition, 1D Laplacian equals f df transpose, into this equation. Let's see what I get. So the first thing I'm going to do is I'm going to do this same transform on my right-hand side matrix B to get B prime. I'm going to do the FFT from the left, from the right, and I'll get B prime. So let me just substitute that in there now. So I'm going to substitute L1. So I'm going to take this and substitute L1 equals f df transpose. And that's what I get. And on this side, I get, I substitute B equals f B prime f transpose. Now I see every one of these 3 terms, I can factor out an f from the left. So let me factor it out. I can factor out f transpose, which happens to be f inverse from the right. And if I throw those away, I get a diagonal system of equations to solve. So now what I need to do, so B prime is the matrix I got from doing the 2D FFT. D is this diagonal matrix of eigenvalues. And X prime is a transform of the unknowns. So all I have to do now is to solve a diagonal system of equations with n squared unknowns. That's cheap anyway, so there it is. I can get each entry of X prime by taking each entry of B prime and dividing it by the sum of 2 of these guys. So that gives me all the entries of X prime. And to go backwards, let me get it right here, I just have to do the 2D FFT again to go from X prime to X. So the algorithm is 3 steps. Do a 2D FFT on the right-hand side, divide each entry by a constant, and then do the 2D FFT again. So very simple algorithm. And so the cost is 2 2D FFTs plus n squared additions of those sizes and then divisions. So it's all n squared log n. And so that's the algorithm that I want to parallelize. And 3D is completely analogous. And so now I've told you everything there is to know about this line. So this is the table of all my ways of solving the Poisson equation. And I haven't told you why I can do it so fast yet, but it's n squared log, it's going to be n log n by the time I give you the algorithm. So any questions about the math of solving Poisson before I now, hopefully well motivated, go on and say, how do I actually do this FFT? So even though I'm only going to tell you about the FFT with those omegas to a power in it, there are a lot of related transforms, and every idea I'm going to tell you applies to them well. So as you saw from Poisson, I have to multiply not just by f, but by f inverse. And the good news is f inverse is basically f transpose, or the complex conjugate. It amounts to the same thing. So every trick for multiplying by f, I can apply it to the complex conjugate with almost no changes, and that multiplies by f inverse. So either one is fine. The other thing is that sometimes I don't want complex numbers. I just want the imaginary part. That's what I actually use to do Poisson. That's just the imaginary part. That's called the sine transform because all the entries are sines. And for JPEG, I only want the cosines. I only want the real parts, and all the math goes there too. I'm just going to stick with the complex arithmetic because it's going to make it easier. So let me just tell you what the serial algorithm is for the FFT and then proceed on to parallelize it. And please ask questions. So this is probably a review for some of you, but please ask questions. So what I'm going to do to do the FFT in n log n time is I'm going to convert the problem of doing this matrix vector multiply to evaluating a polynomial. And so if this is going to be an m, if this is an m by m FFT, the polynomial is going to have m coefficients in it, and I'm going to evaluate it at m points. So that's going to be the conversion. And why am I going to do that? Because I'm going to do divide and conquer. I'm going to take this polynomial evaluation problem of size m and break it into 2 polynomial evaluation problems of size m over 2. Do that recursively, it'll turn into m log m. But this is just the easiest notation. So let me just change the FFT into polynomial evaluation. So there's my matrix times my vector, and there's the jth component. Let me just multiply it out. So this is just the dot product of the jth row of f, the Fourier transform, times vector v. And let me just plug in what is the jkth entry. It's omega to the jkth power. And let me just put in some parentheses. And so now I can recognize this as evaluating a polynomial. The coefficients of the polynomial are the entries of the vector. And the point at which I'm evaluating it is omega to the j. So it's omega to the j to the 0 times v0, omega to the j to the 1th times v1. So there's my polynomial. So the coefficients are the v's, and the points at which I'm evaluating it are omega to the 0, omega to the 1, omega to the 2, all the omega to the j's. So this is just notation. And so what I need to do now is explain to you how I can take the problem of evaluating a polynomial with m coefficients at m points and break it into two problems of half the size. So I can do divide and conquer. And I'm going to have to take advantage of the fact that I'm doing it at these special points that are going to be roots of unity. So here on one slide is how I do the divide and conquer. So there's the polynomial again, evaluating this polynomial with the coefficients v at all these points. And to break it into two parts, I'm just going to take the even numbered coefficients and the odd numbered coefficients and break them into two halves. So v0, v2, v4 multiplied by even powers of x. And there's v1 times x, v3 times x cubed, the odd powers. All of these have a common, since they're all x to an odd number, they have a common factor of x. Let me pull that out front. And so what I'm doing here, you can see, is I'm evaluating a polynomial just with the even coefficients, v sub even, and I'm evaluating it at x squared to the 1 power, x squared to the 2 power, and so forth. So that's a polynomial of with half as many coefficients. And there's the polynomial with the odd coefficients, v1, 3, 5, and again, I'm only evaluating it at, it's a polynomial of half the size. So that's not quite the whole answer, remember, because I want to change my problem of size m is evaluate a polynomial with m coefficients at m points. Here I have two problems, evaluate a polynomial with m over 2 coefficients, but I'm still doing it at m points, right? I haven't gotten that complexity down yet. So here, and the m points are just omega to the j for all these values. But here's the trick, and here's where we take advantage of the fact that it's the FFT. If I take all of these powers of omega and square them, right, because it's of x squared, they come in plus minus pairs. So when I square them, the plus minus pairs map to the same square, and I only have half as many points. And I'm just sort of writing it down there. So omega to the 0, omega to the 1, omega to the 2, all the way up to half of them. If I square them, I get the same as if I squared the last half. And so this is really only a problem of half the size. That's only a problem of half the size. And so now I'm all ready to write down divide and conquer. And so here is divide and conquer on one slide. There's the algorithm. And this is all you need to know. So it's an FFT, it's going to be recursive, so it'll call itself. I pass in the coefficients, I pass in omega, and just to make it easy to read the code, I'll also pass in m. And since I'm doing divide and conquer with dividing the problem in half at each step, I'm going to assume m is a power of 2. Now in the real world, and this is how it was originally invented, in the real world people have m's that are not powers of 2, and I'll say a little bit about that later. So what's the base case in my divide and conquer? If it's just a polynomial of degree 1, then the answer is just v0. There's no work to do. Otherwise, I take the even numbered coefficients. This is MATLAB notation. So this is v sub 0, v sub 2, v sub 4, etc. I evaluate it. So that's a problem of half as many coefficients. So it's m over 2 instead of m. It's evaluated at omega squared. So that's that x squared there turns into omega squared there. So I do the evens and the odds, two problems of half the size. And then I have to evaluate this formula, the even plus the odd, and the odd gets multiplied by x. And so that is now I'm using MATLAB notation. So I take this vector of x's and do a component-wise multiply by the odd values, and then I add that to the evens. So this line of code corresponds exactly to this formula. And but the fun part is that the other values, it's just the negative of one another, because these come in plus minus pairs, as I said, so it's just minus that for the other half. So I really only have to do half as many multiplies and then do a plus and a minus. So how much does this cost? The time or let's say the number of floating point operations to do this algorithm, that's T of m. I call itself twice recursively, so it's 2 times the cost of a problem of half the size. And then this is just, m multiplies and m adds, so plus order m, and that recursion has an order m log n solution. So that's all we need to know to make it run fast. So it's interesting how this algorithm was invented. Back in the early 60s, there was a meeting at some agency in Washington, and there was a guy there named Dick Garwin from IBM who was telling all these folks that they were having trouble because there was a bottleneck. This very special matrix vector multiply was taking up all the time in their signal processing applications. And there was another guy in this committee as a consultant whose name was Tukey from Princeton. He said, I've been teaching this for years, it's trivial. And he wrote it down in the back of an envelope and handed it to Garwin. And Garwin went back to IBM and found a programmer to program it up named Cooley. And when they programmed it up and realized what it meant, they realized it was going to change everything. And then Garwin got worried because he knew that Tukey was a consultant for Bell Labs. And he was afraid that Bell Labs would patent it. So he wanted to make sure it got published, so it was all in the public domain. So he had Cooley write up a paper and put Tukey's name on it and send it to Tukey and say, would you mind publishing this? And so Tukey's response was, who cares? I mean, Gauss knew about it. He didn't bother publishing it. It was in his notes. I don't care. Go ahead. And so it was published, and that was the FFT. So it's been around for a long time, but it only became sort of well-known almost by accident. OK, so, and it's been, had a lot of impact ever since. So now, this is the simplest way to write down the algorithm. It's a few lines of code. And now let's think about, go one more level of details to what arithmetic it's actually doing on which operations, so we can think about how to parallelize it. And so let me take one step in that direction by writing out the entire tree of who's operating on whom. So here's the FFT, and I'm just going to do it for 16 operands, so a vector of size 16. And so that means the V is indexed by 0 through 15. And the nice thing about 0 through 15 is I can represent it by a 4-bit binary number. So for all the different values of x being 0 or 1, and it's looking at these x's is going to tell me how to parallelize it. This is the input. Then the recursion says, please take the even parts and please take the odd parts and call it recursively. So if I have a binary number, how do I tell if it's odd or even? That's pretty easy. I just look at the bottom bit. So the odd parts are just all the bits of the form bit, bit, bit 1. And the even ones are bit, bit, bit 0. So I pass the evens and the odds there. Now, when I do it recursively again, how do I tell what the even ones here are now? Which bit do I look at? I just look at the next bit. So the next bit being 0 means the even subset of this even subset all ends in double zeros. And the odd subset of that even subset ends in 1, 0. And so forth. So at each level of the recursion tree, I pick one more bit. And finally, at the bottom, I have everything multiplied out. And this is the end of the recursion, so I finally do some arithmetic. I finally do some math at the stuff at the bottom of the tree before I propagate it back up. So let's look at the bottom of the tree and ask ourselves, in what order is this data? Because this is going to be the order in which the answer comes out at the end. It goes 0, 8, 4, 12, 2, 10. It's not in increasing order. So what order is it? And there's a hint on the slide written in red. So it turns out that if you take the bits in all of these numbers, they're in order if you read them backwards. So 0, 0, 0, 0, 1, 0, 0, 0, it's just all backwards. So when the answer finally comes out at the end of this algorithm, it's going to be the right answer in bit reverse order. And so we'll have to take that into account when we use it. It's not going to be a big deal, but you have to be aware of it, that's how the answer naturally comes out. And so this is going to motivate the communication pattern on the next slide. So now what I want to do is, let's assume I do this in parallel. And so the natural thing is I can do everything at the bottom of the tree. If I have a big enough parallel machine, I can do all of those in one parallel step. Then I can do everything at the next level of the tree, once they return to give me values at that level, then at that level, then at that level. And so what I care about is, where does the data go? I mean, the arithmetic's really easy. The arithmetic is, a multiply and an add. But what I care about is where the data has to live. So here's a picture of who depends on whom. And so each of these columns of 16 points corresponds to one level in the tree. Here is the initial data. Once I get to the bottom and I've decided who has to be combined with whom. So there's one row of, there's the initial data. There's one row of multiply adds. There's another row of multiply adds. There's another one. And the answer comes out as this column over here. And what I've drawn here, what are all these lines? They say who depends on whom. So this particular entry depends on 0, 0, 0, 0, and, follow the line down, 1, 0, 0, 0. So this is combined 0 and 8. So this is down here. I combine 0 and 8, and I add one of them and I subtract one of them. And so the 0, 0, 0, 0 value will be computed, and the 1, 0, 0 value will be computed. So this dependency here, it looks like this little pattern, that's called a butterfly. So this is the butterfly algorithm because of that dependence. And you can see there's butterflies everywhere throughout here. I'm just looking at the black one. So what's the next level of the tree? The next level of the tree, these things differ in their third bit, not the fourth bit. So these differ by 4. Okay, so let's go look at the next level of the tree. This guy, so I'm looking at 0, 0, 0, 0, and 0, 1, 0, 0. That's 4. And so now I again have a butterfly, but it's of half the size. If I go up the tree one more level, excuse me, then it differs in that bit. So the two guys you combine differ by 2, so the butterfly is half the size. And at the very end, this is just the odd-even part. So so at the very top of the tree, at the beginning of the recursion, I take the evens and I combine them with the odds. And that's exactly what's happening here. This goes, even, odd, even, odd, even, odd. And I'm just combining with my neighbor. So that's what all the dependencies are. And so if I had a perfect parallel machine, and I've just color-coded everything. I'll use the colors for a purpose in a moment. So you can see all the different butterflies of the whole algorithm. So every of these pairs of lines coming together means a multiply and an add. And so if I had a perfect parallel machine with, in this case, 16 processors, in one step I would do the first column, and another step I do the next column, another step I do the next column, and after log m steps I'd be done in my perfect parallel machine where communication was free, which of course is not how it works. So now what I need to do is ask, how do I assign this to a subset of, to a small number of processors and get them all to cooperate and minimize the communication? So I'm going to, again, appeal to something we talked about before, which is there were two natural ways to lay out matrices or vectors. One of them was called blocked, and one of them was called cyclic. And I'm going to use the same idea here. So what was the blocked one? I just, if I had 4 processors, I just divide them into 4 equal chunks. That was the blocked algorithm. And there's also something called cyclic. So how did cyclic work? If I had 4 processors, I'd assign them, just deal them out like a deck of cards. So this guy would go to processor 0, 1, 2, 3, 0, 1, 2, 3. So let me just show you both of them and see what the pros and cons are of those two possibilities. So let me do the simplest one first, which is a blocked layout. So now I have 4 processors, and I've color-coded what each processor is responsible for computing. So the green processor is responsible for that. It owns those 4 inputs, and its job is to compute everything and produce those 4 outputs, and the blue processor similarly. And so what I've done now is I've colored the edges in 2 different ways. So here, the green processor is supposed to compute that guy. He owns both the operands. So I've colored that butterfly green. There's no communication. Now, what about this guy? In this case, the green processor is responsible for him. He owns one of the data points, but the other one is on, if I follow the edge, is on the blue processor. He's right there. So he owns that guy, he owns that guy. So communication is required. So everybody up here, and the pattern is very simple. The first log p steps, where p is the number of processors, every last operation requires communication. And then the rest of it, the last log m over p processors, there's no communication whatsoever. Everything's perfect. Each of these is a call to a local FFT, which you can tune the heck out of, right? So it's 4 embarrassingly parallel local FFTs. That's as good as you're going to get. And this is really bad because it's all communication. Okay, so blocked is good there and bad there. Let me look at cyclic and see what happens. So I've done the same color coding for the cyclic layout. And so now the green processor owns every 4th entry, starting with 0, and the blue processor owns every 4th entry, starting with 1. And now the picture has kind of reversed itself. The first log m over p steps, there's no communication. So if processor 0 needs to compute that guy, and he owns that operand, and I follow that green edge down there, and yes, lo and behold, he owns that green operand. So there's no communication required for the first log m over p steps. But the last log p steps, it's all communication again. So it seems like I win and I lose in 2 different ways there. So, but let me write down, what I'd like, of course, is the best of both worlds. So, but let me now, before I tell you how to get the best of both worlds, write down the complexity of what I just did, either one of those. So I'll just write down a very simple model. I'll say, how many flops, how many messages, how many words do I move for either of these 2 algorithms? And so this is going to be the model we usually use. So m is the vector size, p is the number of processors. I'll just let the time per flop be 1 for simplicity. Alpha is the time per message, beta is the time per word. And so both of these, it turns out, have exactly the same cost in this model. So the time for either the block layout or the cyclic layout. The floating point operations are perfectly parallel because every processor did exactly one piece of the work. So it's 2m log m actually complex additions and multiplies, perfectly divided by p. There's going to be one message per stage because each of these black lines constitutes a message, and there's exactly log p stages. So there's log p messages, each one costs alpha. And then how big is each of these guys? It turns out that, if you follow this, then everything is sort of packed. So the green guy has to send, at this level, has to send everything he owns to exactly one other processor. So that's that's good. It's not like he has to split up his stuff and send a little bit to everybody else. And how much does he send? Everything he owns, that's m over p, because everybody owns m over p data. And he's doing that at log p stages, so there's the bandwidth cost. Okay, and it doesn't matter whether it's the blocked or the cyclic. So the speed up is perfect for flops. You have log p messages, and you have m over p log p word sent. So now, how do I hopefully get the best of both worlds? What I'm going to do is change layouts in the middle of the algorithm. So I'm going to start with a cyclic layout, run that for a while, no communication. Then I get to the point where it's ended. I have to communicate. And then what I'm going to do is transpose the data. I'm going to change all the data structure so it becomes blocked. And then I can run in an embarrassingly parallel way again. And everybody's just doing their local, highly tuned FFTs. So what I need to do is take this layout where the green processor owns every fourth to where the green processor owns the first four. And so that is going to be, I'm going to pay for that. I have to tell you how much that costs. But now I hope you see that on either end, it's going to go as fast as possible. There's going to be no more communication. It's just going to be locally tuned FFTs. So I call this transformation of going from a cyclic layout to a blocked layout a transpose. And that's because it's exactly what transposing a matrix would look like. So let me just show you on one slide why that is. So I'm just going to, so here's the picture. So who owns what in a block layout? In a block layout, processor 0, the green guy, owns the first 4. Processor 1 owns the next 4. So there I've indicated the indices that he owns. So what about the cyclic layout? What is processor 0 supposed to own? It's supposed to own every 4. So 0, 4, 8, 12, and so forth. So let me now look at that matrix of indices and that matrix of indices. They're just transposes of one another. So that's what I need to do. So the question is, how much does it cost to do that transpose in the middle? And so let me do kind of a simplified model of how much it costs. And then we're going to have to, and it won't look good. And then it turns out there's going to be a lot of optimizations to make the transpose go fast. And that's where a lot of work has gone. So let's suppose that I'm not allowed to overlap or pipeline or do any of that stuff. And just say, just do the most naive possible transpose, which will be a bad overestimate of how much it costs. Well, so here's the time to do the whole thing with a transpose in the middle, the transpose FFT. The arithmetic's the same as before, perfectly parallel. The communication, the number of words has gone down actually by a factor of log p because I'm only doing this motion once, not log p times. And it's instead of m over p log p, it's roughly m over p, a little bit smaller. But now this is where the overestimate, and it looks bad. I'm going from log p messages to p minus 1 messages, right? Because when I do a transpose, I have to send a little bit of what I own to everybody else, right? So processor 0 has to send 1 to processor 1, 2 to processor 2, and 3 to processor 3. This is all happening in one step. And so it looks like I'm doing p minus 1 messages. So that does not look like a win, does it? Going from log p to p minus 1. Well, the good news is that there's an enormous amount of overlap possible of communication and computation if I do this right. So in fact, what people do in practice is that they overlap these transposes with doing the local FFTs. So they make a little bit of local progress on their local FFTs, then they start sending a message. And then they do a little bit more arithmetic and they start sending a message. And by doing that, it turns out you can hide this, and it looks like you're only sending one message on a lot of current machines. So this is the tuning space. It depends a lot on the individual hardware parameters. And so now, to make progress, I have to go down one more level to say how people actually optimize this. And I'm not going to do all the details, but I give you all these references for the details. Now, before I leave this, go on to more parallel FFT, let me tell you what is known about the provably optimal way to do the sequential FFT. So optimal in the sense that I'm going to do this algorithm, m log m, floating point operations, but I want to minimize the amount of traffic to memory, right? So my measure of complexity now, just like for matrix multiply, how much data do I have to move between DRAM and cache? And there's a theorem, and it turns out that by emulating the parallel algorithm in the serial case, we'll attain the lower bound. So here's the lower bound. And it's actually from the same paper that first wrote down the matrix multiply lower bound. So suppose I have, I want to do the FFT, the divide and conquer algorithm I just showed you. It's a vector of size m. It doesn't fit in my cache. Cache is size capital M. Then the number of words that I have to move between fast and slow memory, no matter how I do it, is the number of flops divided by the log of the cache size. So that is, not nearly as good as matrix multiply, right? Matrix multiply was the square root of m, and this is the best we can do. And the proof follows by looking at the fact that each word of data is only reused log capital M times. It's just, that's just the nature of the algorithm, unlike matrix multiply, where every number gets used many, many times. So the question is, how do I attain it? And it turns out that if I have a sequential algorithm that simulates the parallel algorithm running the transpose algorithm, that will minimize communication. So here is the idea. So imagine, so we're going to have my sequential algorithm is going to pretend that it's going to emulate a machine, a parallel machine with this many processors, so that each processor stores and is going to work on that many words. That's what the sequential processor has in its cache, capital M. So what the sequential processor is going to do, it's going to run this algorithm. It's going to do what the green processor would do, all of that, finish it, put it back into main memory. Then it's going to run the blue algorithm, do everything the blue processor would do, then the magenta, and then the brown. Then it'll do what the green processor would do, then the blue, then the magenta, then the brown. And everything at each of these levels, if I pick the number of processors right, will all run in cache. So each one of these color-coded subsets of the butterflies is all going to run in cache. And so that will hit the lower bound. And it turns out, if you just do it the recursive algorithm in the cache oblivious fashion, where you don't actually think about where it is, it will attain that. And that's going to be the trick that's used by this auto-tuning FFTW code. It's just going to do divide and conquer, and it's going to traverse the divide and conquer tree in the right order. You have to be careful to do it in the right order. And it will automatically, without even knowing what the cache size is, hit the lower bound. So when we talked about matrix multiply, we also talked about divide and conquer matrix multiply and how it could hit the lower bound just by dividing your matrix into 4 matrices of half the size and multiplying them recursively. It's the same idea. And it works very well. But let's go back to the parallel FFT and sort of describe how that's going to work. So the algorithm that I showed you, the transpose FFT, is going to leave the data in bit reversed order. So let's just think about whether that's a problem. And sometimes that's perfectly fine. Let's suppose I'm doing Poisson's equation. I do the FFT, I get my answer in a funny order, I'm just going to divide each entry by the diagonals of the eigenvalue matrix. So back here, when I did Poisson's equation, let me go back to it. So here, this matrix is going to have a very funny order. It's not going to be the original matrix. It's going to be, all the row and column indices are going to be permuted. But I still just divide each one by a scalar. I just have to pick the right scalar. That's not a problem. So now, what happens when I run the FFT again, where the input is in bit reversed order? That means I'm going to bit reverse it again. So I go from input is regular to output is bit reversed, then input is bit reversed, and what's the output? What happens when I bit reverse twice? It comes back to the original order, right? So the output comes out perfect. I don't have to even think about it. So that's very nice, and it's often that you do FFTs in these pairs, and so everything is just fine. So let me just, before I leave this sort of basic study of the FFT, mention that there are other algorithms which are completely different. The one I just want to mention, this is an idea due to Alan Edelman. He wrote down a long time ago. And it's actually based on the fast multipole algorithm. So what he does is he thinks of all the roots of unity as being points in the unit circle. And the idea is that if a point is far away, if it's a little white dot up in the sky, but it's, if you're far away in the unit circle, a big angle away, it can approximate you, just in a similar idea that the fast multipole does. And so he actually comes up with a new algorithm which approximates the FFT, and it can do much, much less communication, just in the same spirit that the fast multipole method can do a lot less communication by approximating things that are far away. So this is, I would say, not yet practical, but I just wanted to mention it before I go on to optimize the communication of the usual FFT, which is what people do today. So there are other interesting possibilities in the future. Okay, so let's go on to, yes, question. And there's a microphone.
Why did you mention that it wasn't practical?
Because right now, the arithmetic count is much bigger than 2m log m. And so that is not yet compensated for by doing less communication, compared to all of the work that people have put into making classical FFT run very fast. In fact, in the data that we'll see, by the time people have finished optimizing the 3D FFT, it spends, at most maybe half its time doing communicating. And so even if the communication were free, you'd only get a speed up of 2. And so if you're doing a lot more arithmetic, that would compensate for that possible speed, that would undo the possible speed up of 2. So now I'll give you lots of data in a moment. I have lots of measurements on different machines of different ways of tuning this. Okay. Just to mention, so I'm going to concentrate on the 3-dimensional FFT, in part because there's sort of a standard contest, just like people race for the top 500 for LinPack, who can solve AX equal B the fastest. There's a similar race for who can do the fastest 3D FFT. And so I will show you some of the tuning techniques that people have used to make that go fast. Let me just talk about the 2D case first to illustrate the tuning space, and then I'll go on to the 3D case. So remember, 2D FFT is do FFT in all the columns and then all the rows, or the other order. So how am I going to do that? So one way to imagine, obvious way to do a 2D FFT, is I do a block layout for the matrix. So I break up my matrix into blocks where there's, it's a square root of P by square root of P grid. And then I can do a parallel FFT for each row using the algorithm I just showed you, and a parallel FFT for each column, and it's just call the algorithm I just showed you a whole bunch of times. And now that's not necessarily a good idea. So here's the second idea. Let me start with a row layout of the matrix. So every processor owns one piece of the rows. And now I can do all the row FFTs, totally embarrassingly parallel, and no communication whatsoever, finish all those. And then I transpose the matrix. So every processor now owns a block of columns, and I do all the FFTs, the column FFTs, again, embarrassingly parallel. So that's a natural way to do it. And then there's a third option, which is start with the rows. Every processor owns a bunch of n over p rows, do all those independently, and then do the parallel FFTs of the columns without changing the layout. So leave it in a row block layout, but do now parallel column FFTs. So it turns out that of all these options, the middle guy is the best, especially if I manage to overlap the communication, the computation. So I'm going to start with a row layout, do all independent FFTs, and then start transposing it while I'm still finishing other rows. So for example, I can do the first row that a processor owns, finish that FFT, and then start sending it to everybody else while I'm doing the second row FFT. And so I can have everything going on at the same time, and that's going to be the trick that works. And in fact, I'm going to show you this in the case of the 3-dimensional FFT, just because that's what everybody likes to work on. And so the analogous case here is that I will finish doing all the FFTs in 2 directions, and then start transposing to do the FFT in the 3rd direction. Okay, so the reason I have to do, so now I'm going to get sort of more into how the hardware works and what opportunities I have for overlap. And in fact, I'm going to show you a performance model that's more detailed than the ones I've shown you before. So far I've just counted messages and counted words. And I've kind of waved my hands and said, that's good enough. If you overlap, then it only improves by a factor of 2. Who cares? Well, now I care about that factor of 2. So I'm going to use one more level of detail about what can happen in parallel on a processor in terms of communication and computation. And I have to worry about this because, a transpose, everybody has to talk to everybody. And there's a limit to how big people are willing to build networks. Nobody will let you simultaneously have everybody talk to everybody. How many wires would I need to do that? Every processor would have to be connected to everybody else. That would be like p squared wires for p processors. Nobody builds those things. There's always a limit, and that limit is called the bisection bandwidth of a network. And so for any network, you can ask, suppose I divide the processors into 2 halves any way I like. What's the limit of how much can be sent back and forth between the top half and the bottom half? What's the the sort of the bottleneck, the worst way to cut my processors into two halves. That's called a bisection bandwidth. And that will limit a transpose. That sort of gives you a lower bound on how fast transposes have to go. And so, and as I said, people aren't building them big enough to do that in one time step, so we have to do a lot of overlap. So now, let me, with that motivation, go on to the next level detailed model. And this is called the LogGP model. And so this is sort of the next level of detail about what processors can do in parallel locally. And so here is a timeline of what one processor can do to communicate with another. So the vertical axis is time. This column tells me what processor 0 is doing. This column is the timeline for what processor 1 is doing. And so what actually happens when processor 0 wants to send a message to processor 1? So they're actually, right now I've just said there's alpha and beta. It's actually a little bit more complicated. And so what processor 0 does, it has to pack up the message and get ready to send it. I'm calling that O for overhead of the send time. That keeps that processor busy. He can't do anything else. Then he ships it into the network, and there's some other processor, maybe a network interface card, that's now, the CPU has handed over its responsibility to another piece of hardware, and I now have the latency, L for latency, and it's transferring over the network. At this point, processor 0 is free to go on and do something else. He can start doing FFTs. Now, what about processor 1? Processor 1 isn't doing anything until that message actually arrives, and then processor 1 is busy. There's overhead there to receive it, to unpack the message. So so all of this time from there to there, processor 0 is free to do other stuff. And all of that time there, processor 1 is free to do other stuff. So that's our opportunity. So that's assuming that there's no overlap in messages. But now, remember, I'm probably going to be sending something big. So the question is, let's suppose I need to send a lot of stuff to processor 1. So I'm going to try to pump messages. I'm going to pipeline messages from processor 0 to processor 1. What does that look like? Well, here's the first message. It goes just the way it did over here. So this graph of who's busy when is the same. Now, when can processor 0 start sending the next message? Well, there's another parameter called the gap. And the gap is essentially beta. So it's just, this is older paper, they called it G, we call it beta. So the processor 0 can start sending the next message after waiting for this G for gap, or reciprocal bandwidth. And then he can start packing up the next message. It gets shipped over, processor 1. And so if I want to send a long message, it's G that's going to tell me how fast it can go. Now, where is the possibility for overlapping communication and computation? Here, if I look at the timeline for processor 0, he's busy, he's free. He's busy, he's free. So it's the difference between the gap and the send overhead. That's where I can do FFTs or other useful work. And so what I want to do is just show you some measurements of all these numbers on a few machines now to show you how much opportunity there is to do this overlapping. And then the algorithm will take advantage of it. So these are just going to be benchmarks which try to tell us what a bunch of these numbers are. And so here are the benchmarks on maybe some historical machines and some more modern ones. And the machines come in various pairs, groups. So this is a Cray T3E with 3 different ways of sending messages, because there's good ways and bad ways. Here's an IBM SP, I think it was, with 2 different software messaging systems. I mean, so the innovation, the hardware doesn't change, but how you use the hardware changes. And there's a Quadrix network, a MirNet, and a gigabit Ethernet. So it's color code, and so the vertical axis is time, so down is good. And it's color coded by what is going on in this picture. So green is the latency. That's the time the network is actually busy, but the other processors are not. The send overhead, that's when processor 0 is busy. So this time here, that's O send. And so that's when processor 0 can't do anything else. And the yellow is the receive overhead, which is smaller. That's when the receiving processor is busy. Now, so what is my opportunity for doing overlap? It is, if I come back to this picture here, it's this gap in here. So it's L plus O receive. So if I do this right, it's going to be green plus yellow. So green plus yellow is the free time that processor 0 has to do some useful work, FFTs. He's only occupied during the blue time. And so you can see that all of these different platforms give lots of opportunity. So what is this hatched line here? It's because on this particular platform, which was a not very well optimized version of MPI, if I come back to this picture, this send time and this receive time, they overlapped. These two processors started talking together and shaking hands and saying, oh, do you have enough room for me to send your message? Yes, I do. So they have a conversation, so they're both busy. And they're both busy for a long time on that particular platform. That wasn't a very good one. So, but these are the opportunities, green plus yellow, that we have for doing overlapping communication and computation. So there's a lot of details in how you actually do this benchmarking, and I have that information in the backup slides, but I don't want to go into it right now. So so now let me try to take advantage of that. So again, overlapping can mean several flavors of overlapping, and for me, it's going to be overlapping communication and computation. And as I said, the overlap potential when I send very, very many messages, let me come back here, is, so this I showed you the data for just sending one message. Here, if I'm sending a lot of messages, it's going to be the difference between that point and that point. That's when processor 0 is going to be free to do something useful. And so what does the hardware have to do for this to actually be useful? What I need is what's called send-side direct memory access. I need some hardware support so that I just have to tell this extra processor that, oh, here's where my message starts in main memory, here's where it ends, you go please ship it off, right? Just give it some instructions and go ship it off. So modern processors have that. The potential grows as the message size grows because then that other hardware, the network interface card, can spend more time doing it. And the remote overhead on some machines can be 0 if you have remote direct memory access. If that network interface card gets the message, and if that message says, oh, here's where you're supposed to put it in memory, the network interface card can just put it in its destination. This is how UPC works without even bothering the CPU, right? So that's, but obviously you need a lot of good software support of the kind that was built in underneath UPC to make all of this work. And so what is the interface? And you've been using it already this semester. It's called GASNet. That's what lives under UPC in order to let you do all of this stuff. So GASNet is global address space of the network layer. And so it doesn't require the CPU to be involved in sending messages. If there's hardware there in the network interface to move the data back and forth, it will take advantage of it. So the message contains a remote address, so there's no receive overhead. And this is what I want to compare on the next few slides to MPI, and then eventually have the FFT running in UPC and compare that to FFT running in MPI and see how much faster we go by letting the extra overlap opportunities from UPC to take advantage of that. So let me do another benchmark, which is how fast it takes to send a bunch of messages from one processor to the other on GASNet versus MPI. So in this case, I'm sending a very big message, a lot of data from one processor to another, but I'm going to break it up into chunks of different sizes. So I think I'm sending 2 megabytes in here, and I can either send that as a single 2 megabyte message or 200 megabyte messages or 100,000 megabyte messages all the way down to a gazillion 10 byte messages. So that's what the horizontal axis is. How do I break it up? And the vertical axis is the bandwidth, so up is good. And so and the blue line is UPC, and the red line is MPI. And so blue beats red. And so, but let's look and see when it particularly beats it. So if I just send one enormous message, then they're both limited by the hardware bandwidth on the network, and they're both running at about the same. But at some point, you have some buffer problems in MPI, so it slows down a little bit, whereas GASNet does not. So now let me send more smaller messages. You can see and that means I'm going to move from right to left. And as I do that, GASNet doesn't slow down very much. It keeps getting a pretty high bandwidth, but MPI slows down significantly. So if I come down to here, and I have the ratio of blue to red on this green curve, if I come down to about here, then UPC is twice as fast as MPI. So, and it's getting a pretty high fraction of peak. So this says that if I send my 2 megabytes as many, many 1,000 byte messages, I will go much faster than MPI. I will go almost at the peak speed, and by pipelining it that way, by sending lots of little messages, I will have a lot of free time, a lot of opportunity to overlap communication and computation. So the more small messages I send, the more opportunity I have to overlap communication and computation, the more of these spaces I have. I will have more and more of those. But I can't just keep making it smaller forever, because then I will lose the total bandwidth. So right around here is the sweet spot. If I send lots of messages this size, I'll get nearly the peak speed of bandwidth of the machine. I'll go a lot faster than MPI, and I will be able to have lots of communication and computation overlap. So the tuning parameter for my algorithm is going to be, what size messages do I send in the middle of the FFT? So here is just one more way to measure this data. And so again, now it's a whole bunch of different machines. And so this is actually different networks with different processors. And this is the vertical axis is percent of machine peak. And it's comparing MPI to GASNet. And you can see the red bar, GASNet, is always much faster than MPI. So this is more, bragging how well GASNet works compared to MPI. But this is the opportunity we want to take advantage of. So now let's get back to the FFT and think about all the different ways of doing the FFT to take advantage of that stuff that I just showed you. And so the bottleneck is going to be this transpose. I'll draw pictures of where the transpose goes. And so what I want to do is overlap the communication cost of the transpose with doing more FFTs locally. And this design space, I'm going to show you pictures of this three-dimensional grid. And this is based on a benchmark that you can download from NASA. It's called the NAS Parallel Benchmark Fourier Transform Study. And again, people have a race to see who has the fastest 3D Fourier transform. It doesn't quite get as much publicity as solving linear equations, but it's out there too. And this particular project started as the CS267 project a number of years ago. And for a while, it was the fastest FFT. I mean, people have gone on to optimize it, but these basic optimizations are part of what people do now. So here is my 3D grid that I want to do my 3D FFT on. And it will be square when I show you the final data, but in general, it could be three different dimensions. And so I want to do FFTs in the x direction. So I will have ny times nz, embarrassingly parallel FFTs in that direction. I will have FFTs of length ny, lots of them, nx times nz in that direction, and I'll have FFTs in the z direction, nx times ny of them. And so here is the simplest 1D layout that I'm going to start with. And I'm going to have to change this layout to make it run faster. So let's suppose I have 4 processors, all color-coded, and each processor gets a quarter of these XY planes. So what can I do in parallel with no communication? I can do all the FFTs in that direction. I can do all the FFTs in that direction. But now I have to communicate, do the FFTs in the z direction. So the question is, so let me just, I think I just said this. So I'm going to start by doing all the FFTs locally in that direction, no communication, then the FFTs in that direction. And then I have to communicate to make it work in that direction. So let me show you sort of the simplest way to get the transpose to work. And so what I would ideally do then is, in order to do the FFTs in this z direction, in and out of the plane, this is what each processor should own. So let me just ask, what does the light blue processor in front have to send to everybody else? Well, he's going to keep the top quarter of that slab that he owns. The next quarter of the slab is going to have to be sent to the orange processor because he owns that. The third quarter of his slab will be sent to the yellow processor, and the bottom quarter of his slab will be sent to the blue processor. And so the question is, how do I break that transpose up so that I can do that overlapping with all the many, many FFTs into which this is packed? Okay, so I'm going to explore 3 different ways to overlap the transpose and doing the FFT. And they have 3 names. The first one is packed slabs. And a packed slab is exactly what this whole contraption is. That's called a packed slab. So a slab is a square like that, and packed is that they're all together, everything that I own. A slab is just a single slice, a single plane through it, instead of all of them packed together. And a pencil is just a one-dimensional thing. It's an FFT. So this is 3-dimensional, that's 2-dimensional, and that's 1-dimensional. So a pencil is just enough data to do a single FFT. And so I can imagine doing FFTs on an entire packed slab before I start transposing it. Or I can do it on one slab, start transposing that, work to the next slab. And so what's the difference in communication cost as I sort of explore this design space? And as I go from there to there, I'm going to have an enormous number of more messages because I'm going to break up that packed slab into many, many tiny pencils. but they're going to be much, much smaller, right? So this is going to be, this is going to have a lot more messages. They're going to be a lot smaller. I'll have more opportunity for overlap. What's the sweet spot? So let me just draw the picture of how the algorithm is going to work. And I'm going to assume I have 4 processors. And I'm going to assume I have a 16 by 16 by 16 grid. So it's, I can show you every last point. And so what does one processor own? It owns 1/4 of all of the 16 slabs. So there are 4 out of the 16 slabs. That's owned by one processor. So the first thing he's going to do is perform all of the local FFTs, all the rows and all the columns. So that is 4 times 16 columns and 4 times 16 rows. Finish all of those. All that blue stuff is done. Then decide who gets which. And so it's going to break them up into these pieces. And then all of the stuff here, and I had this picture in the previous slide, everything that's colored orange is going to get packed into one message and sent to the orange processor. Everything colored yellow is going to get packed into one message and sent to the yellow processor, and so forth. And so there are going to be 4 messages, and they're all going to look like that to those particular destinations. And then in UPC lingo, I'm going to do p puts of the data, and it's going to just put, everything that's orange is going to be sent in 1. And to processor 0, and if you're processor 0, that's actually not any communication at all, it's just local, and then to processor 1, to processor 2, and to processor 3. So that's what it all looks like for a very small problem. Let me just show you the numbers for a bigger problem. Let's suppose it's not a 16 cubed problem, but a 512 cubed problem. And let's suppose I have 64 processors. Then how many messages am I going to send? I'm going to send 64 messages, well, except for myself. And each one is going to be as big as possible. It's going to be 512 kilobytes. So let me tell you what happens when you download the code, which is written in Fortran and MPI from NASA, and run it, because that's how that works. So they've carefully optimized that particular algorithm. They call FFTW to make all the local FFTs run as fast as possible. And this is, what's class D mean? They have different sizes. So this is one of the larger benchmarks with 256 processors. And it only got 67% of peak. So if you look at the bandwidth that was attained by sending all these messages around, you could say that's good enough, 67%, but no, we can do a lot better than that. So that's the peak the bandwidth they got when you just take the standard code optimized the way I just showed you. So now let me explore the rest of the design space and see how much faster I can go. So here's what the algorithm is going to look like. And so again, I own 4 of these 16 by 16 slabs, but let me just show you what happens with one. So I'm going to start by doing all the column FFTs. So I will finish all of those. So I'll do 16 local FFTs. And now I start doing the row FFTs. So what I'm going to do is I'm going to finish all of these 4 row FFTs, and then I'm going to send them to processor 0. Then, while I'm sending them to processor 0, I will immediately start doing the next 4 row FFTs. That's going to be the communication computation overlap. And as soon as I'm done with all the orange rows, I will send them to the orange processor, processor 1, and immediately start doing the yellow ones. Well, so now I'm going to have that FFT overlapping with that communication. And then I will overlap that to that. And then I will go on to the second plane. So I'm going to have a pipeline now of so I'm going to have that overlapping with that, that with that, that with that. And that picture repeats itself 4 times, because that's how many planes I own. So that is how much overlap I get. And so if I still have that 512 cubed grid across 64 processors, I'm not going to send 64 messages. I'm going to send 512 messages. And they're going to be much smaller, a factor of, they're going to be 64 kilobytes. So I used to send 64 messages of size 512 kilobytes, and now I sort of swap the sizes, many more messages, much smaller. Their product's the same, right? Because I still have to send the same total amount. So that's the second option. And here's the third option, which is pretty natural. And again, I own 4 planes of size 16 by 16. I start by doing all of the columns. I finish all of those. And so now what I need to do is send the rows, and I want to overlap that. And so I've color-coded by which processor eventually has to get it. So here's the first thing I do. I do the first FFT of the first row, and I immediately start sending it to processor 0. Then I move down, and as soon as that message goes out, I start doing that row, not the next one, but the one that goes to the orange processor. So I do one more FFT, send it to processor 1, move down to the yellow, do him, so this is overlapping with that, start sending it, move down to the blue, start sending it. And so this is, so now you can see I have a lot more pipelining going on. But so why do you think that I'm not doing all the blues followed by all the oranges followed by all the yellows? I mean, I could have pipelined it that way too. But this is better because so the messages would be the same size if I did send 16 messages to processor 0, send 16 more, so send 16 words, send 16 words, send 16 words. Each message would still be just 16 words, but they'd all be going to the same place. There'd be contention, right? So they're all going to pile up on, in the mailbox, so to speak, of processor 0. But here, I'm keeping all of the network busy, right? I'm sort of using all the links by keeping all the messages sort of spread out, by, so that every processor is going to get sort of an equal share of the inputs. And then I just keep working my way through it, right? I just keep walking all the way through until I've done all 16 rows, but I'm sending them, to processor 0, 1, 2, 3, 0, 1, 2, 3. So I'm keeping the whole network busy. So that's going to give me, hopefully I'm going to use all the hardware in the machine there by keeping all the links busy by sort of making sure not everything's trying to get delivered to the same place and creating a bottleneck. And so and then I do the next plane. I just keep going through this process. So now I have lots of little messages, and for that 512 cube grid, I'm sending 4,000 messages, but each one is only 8 kilobytes. So now the question is, am I going to really pay for that by sending all those messages, or do I get more opportunity to overlap communication and computation? So these are the three flavors of algorithm. So there was pencils, there was, oops, too many animations. There was slabs, and there was packed slabs. Okay, so those are the three flavors I want to compare. Lots of animations here, excuse me. Okay, so let me now give you an illustration of just the communication costs. Let me just measure, this is not the whole algorithm, so this is but it's the same size problem, 512 cubed on 64 processors, and I'm just going to measure the communication costs, and this is on a particular platform, and so let me now just do a measurement where, let me make sure I'm explaining this right. So now this is again, so I'm not measuring the exact algorithm yet. I'm telling you what the opportunities are for going faster. So I sort of showed this data before, and I'm sending a lot of messages, a lot of data from one processor to another, and I'm comparing GASNet to MPI, and I'm taking the same message and sending it to lots of little ones, or a few big messages. Now, if I send just one large message, then that's going to be the packed slab, and that's the speed that I'm going to get. So I'm going to be limited by the hardware speed of the machine, but there's going to be no opportunity for overlap. So algorithm 1, the packed slabs, is going to be living over here in terms of how much bandwidth it attains. Now, if I use the slab approach and I send many more messages and they're smaller, that's going to live over here. So now MPI and GASNet are going to run at about the same speed, and I'll have a little bit more opportunity to do overlapping, but not as much as I would like. And then finally here, if I do the pencil trick, that's how big the messages are. GASNet is still sending, getting nearly the peak speed of the machine, but it's going to go a lot faster than MPI, and I'm going to have many more messages, so I'm going to have a lot more opportunity to overlap communication and computation. So this is going to tell me that there's going to be the opportunity for speed up. So just to sort of take this is not the FFT itself, it's sort of the underlying communication that will be used in the transpose in the FFT. So now let me show you the benchmarks of the real data, and this is going to be on 4 platforms. You don't bother reading this. This is just for reproducible science, so I can tell you exactly what the platforms are. Although it's a little bit of a joke to call it reproducible science because none of these machines exist anymore, but in principle it's sort of reproducible. Okay, so now let me compare the 3 algorithms. And so what do I have here? Here, each of these triples are different platforms with different versions of the network. The vertical axis is speed compared to the downloaded MPI plus FFTW code that you get from NASA. So that's 1. And so if it's 1.25, that means it's going 1.25 faster than the downloaded code. And so there are 3 versions here. All of these are written in UPC. The blue is packed slabs, so that's the fewest large messages. The green is slabs, so middle size, more messages. And orange is pencils, so where you send many, many tiny messages. And so you can see, up is good, it gets up to 1.9 times faster than the best possible Fortran plus MPI code by letting all of this overlapping happen. And you get a big benefit by going from packed slabs to slabs, and then you get a little bit more benefit from going all the way to pencils. So that's the total speed up that was gotten. And so the question is, how much was that due to the communication speeding up? So let me just take and extract from this the time doing communication and show that on the next slide. And so these are the same platforms, the same communication, the same platforms. And now I am comparing UPC and MPI, just the communication costs. And so the vertical axis is time, so down is good. And so I'm comparing UPC with slabs, UPC with pencils, MPI with slabs, and MPI with pencils. And so you can see that UPC beats MPI. UPC beats MPI dramatically. In fact, MPI crashed. That's why there's no blue line there, so it didn't even finish. And in all of these cases, UPC beats MPI. But what's a little bit funny is that slabs beat pencils. So just the time doing communicating, slabs look faster than pencils. But on this slide, slabs were slower than pencils, right? So why is that? It's because this is just the communication time. It's not the total time. And by going a little bit faster in communication, I had more opportunity to overlap communication and computation. I could break it up into more little FFTs. And so that's why I got to speed up. Even though they're going from slabs to pencils, it slowed down. It actually sped up because of the overlapping communication and computation. So one more little summary here of the time. So this is, again, all those different platforms. Vertical axis is speed, so up is good. So there's the best tuned version of the Fortran plus MPI. There is the best MPI code, which was always slabs, so that was our own tuned version, or this team's tuned version. And then there was their best UPC code, and that was always pencils. So this was coming from the downloaded code. This was doing tuning there, but insisting on MPI, and this was doing tuning and using UPC, and so it won. So this is on all of these platforms. And I just have 2 more slides to show you the same story and a bunch of other platforms that they did. So again, people have these races all the time. And so here, this was in an IBM Blue Gene P. Vertical axis is gigaflops, up is good. And so again, as you go from packed slabs to slabs, it helps to send more small messages. Let me just skip ahead on this one, and because I don't have that much time left. And go on to Franklin, which is the predecessor to Hopper. And so now I'm comparing, the vertical axis is gigaflops, so up is good. And so there's this funny dividing line. Over here, MPI wins, and over here, UPC with slabs wins, which is what we were predicting would be the case everywhere else. That's because on Franklin, they had specially optimized MPI to be very good with messages of this size. So what is the horizontal axis? It's the problem size. So this is a problem size that's, each time as you go from here to there, the problem size doubles in each dimension. So everything here is smaller, and in particular the messages are smaller, and they had optimized MPI to run on those small problems. But once it got large enough, then everything I was telling you was a good idea. Okay. So that's the story of the 3D FFT, and people are continuing to tune it just because it's important. But as I said, people also build auto-tuners for this stuff. They haven't built auto-tuners for 3D FFTs yet. That's been too hard. But if you've ever typed FFT in MATLAB or any other system, you've probably used this code. And it's an auto-tuner that works very well in the sequential case. And indeed, all the code that was used in these examples, when you do the local FFTs, it's based on this or a version of it. So I just want to tell you what this is. This is called FFTW, which is the fastest Fourier transform in the West. It was a PhD thesis, and it won a prize for most influential numerical software. And it's very similar in spirit to some of the auto-tuners I've told you about before. Basically, you tell it a value of n, which could be an arbitrary number. It doesn't have to be a power of 2. It could be a prime if you like. it will run on your architecture, and it will hand you back sort of this opaque handle, a subroutine specially built for you, which will do your FFT as fast as possible on that just for that value of n and just on your architecture. And there's another, I'll tell you a little bit about another one too, but let me just start with FFTW. It's widely maintained. The last release, I think, came out about a month ago, and it fixed a bunch of bugs and added some new features, so it's still a very widely used code. So let me just use their slides. This is what, so I didn't draw these slides, and sort of give a description of how it works. And so it does real and complex FFTs, and it was originally just in the sequential case, but they've added parallel versions. And it does a lot of automatic generation of code. And so let me show you some performance data and then a little bit about how it does the tuning. And so here are each one of these very large number of curved lines is a different FFT implementation, because over the years many people have tried to implement them. So you can download vast numbers of different FFTs and compare yours. And theirs is on top, and it's the fastest. And for all of these different platforms, but they actually have two versions. And the solid black line is maybe the standard version. That's where you have an input v and an output vector f times v, which is written somewhere else. You don't change v. But you can also run the FFT so that f times v overwrites v. So you can use half as much memory. That's the in-place FFT. And that is the dotted blue line, which is sometimes a little bit faster, sometimes a little bit slower. But you can see that it's doing very well and beating everybody else pretty much. One of the lines here is MKL. So it was the tuned Intel library. I believe that is the black line, and you can see that they're beating MKL. In the meantime, MKL tries to adopt these things. They have a team that works hard at this stuff. But when they were originally doing this benchmark, they were certainly the fastest. So these are all for powers of 2. But FFTW is very flexible. It doesn't depend on powers of 2. So here, if you look at the horizontal axis, you can see there are lots of other funny dimensions that it's trying as well. And now it is significantly faster than MKL, because they have not tried to tune it for every obscure non-power of 2 that people might want. And that's what auto-tuning is for. You want to automate this process so that you don't have to do it carefully by hand. And so now it's beating all the other implementations quite handily, both the two-vector version and the one-vector version. They've also added SIMD instructions. And so here it is, here's adding in, this was on a Pentium with two-way SIMD instructions on SSE2. And there were some places where MKL was the winner, but it was often the winner, as you can see over here, and it was always the winner when it was non-powers of 2. So this is just some advertising data. And of course, since this is a little bit old, and since there's a new release, you can measure it yourself if you want to see how fast it goes. So here is sort of a sketch of how it works. So it has inside of it many different FFT algorithms, because the divide and conquer Cooley-Tukey that I showed you, the classic one, that's one of hundreds. There have been over 100 papers written with different ways to do divide and conquer FFTs and still get M log M. And so they have a lot of that sort of built in, and they explore that as part of the design space, in addition to all the other sort of low-level tuning that one could do. So at every level of the divide and conquer, you could divide and conquer in a different way. And especially if it's not a power of 2, it depends on the prime factorization of your number. And so so when you originally call it, it takes a while, and it has a planner that picks the best composition of what you should do at each divide and conquer level, and by measuring the speeds of all the different computations. And it returns to you a plan, sort of a handle to this sort of black box, which has all that smarts built into it, that you can then call later. And then at the very bottom, it doesn't do divide and conquer all the way down to 1 by 1 or 2 by 2. At some point it says, oh, I'm just going to unroll it completely, a 32 size FFT or a 16 size FFT. And all those codes are automatically searched over by a general purpose compiler. So when I gave you a lecture on OSCI, which was sparse matrix vector multiply, it was very similar in spirit. You break your matrix up into little blocks, 4 by 4, 3 by 3, whatever. Each of those could be completely unrolled in assembly language, and because you don't want to go have a loop of that size, and so they do a very similar thing. And so what does it look like at the software level? It looks very similar to the interface that I showed you for POSCI. What you say is please plan how to do an FFT. It's going to have input X and output X. That tells it that it should plan to use just one copy. It should do the forward FFT, that means F, as opposed to the backward FFT, which is F inverse. And then it says, go ahead and do all the measurements. Run a lot of benchmarks. And it hands you back a plan that says how to do it. And you can reuse that as often as you like. So this can take a long time the first time you do it. And then you can reuse it every time you have a new vector X. And then when you're done, you have to clear it. Just as you deallocate memory, you have to deallocate your plan. And so this is useful because you typically do many, many FFTs of the same size, because every time you do it for a different size, you're going to spend a lot of time. So let me say how the plan is executed, and it's going to do it in a recursive fashion, in a cache-oblivious fashion, to get all the locality. So here is one possible outcome of the plan. You take an FFT, you break into two of size 4, and then you break each of those size 4 into two of size 2. And if you just implement it in the most obvious way, you do everybody at the bottom of the tree, then everybody at the next level, and everybody at the next level. And that would do log n passes over the data, and that would be slow, right? So that would sort of maximize the amount of memory traffic. So the traditional solution is you would have explicit cache blocking. So you would say, I can fit this much of the tree in my cache, so I'll do everything in there. Then I'll move over and do that subset of the tree and work my way up to the top. But in that case, you have to know the size of the cache blocks, and that means you have explicit code. And so instead, what they want to do is be oblivious. And so what they're going to do is divide and conquer, and they're going to do depth first traversal. So they're going to, they'll call FFT at the top. Then that will call the size 4 one. That will call the size 2 one. And you'll automatically have all of this stuff living in cache, and you don't have to know how big the cache is. So that is the magic when cache-oblivious algorithms work well. And so that's what they depend on, rather than changing the cache size for every different platform. And so there is the usual advertising for cache-oblivious algorithms. You don't have to know what the cache size is or how many layers there are. It will do it for you automatically. And then at the very bottom level, you have these things called codelets, which are completely unrolled 16 by 16 or 32 by 32 that are called at the bottom, because you don't want to keep doing divide and conquer all the way to the bottom. So let me just mention one other system, which targets not just fast Fourier transform, but all DSP algorithms. I mean, Viterbi, convolutions, you name it. And at one point, they had a website where you could say, here's my algorithm, here's my size, here's my hardware, please give me back the optimal code. And that has since become a startup, because people are interested in that. And I will let you just read all of their website at spiral.net. So at this point, we have finished pretty much all of those motifs. And we're still going to have a lecture on graph algorithms. That will come soon. But I just want to give you an outline of the rest of the semester, since we're running out of time. So the next lecture is going to be on parallel graph algorithms. That's going to be a guest lecture by Aiden Bullish, who has released his own widely used parallel graph algorithm package. He's a staff scientist at Lawrence Berkeley Labs. I will talk about dynamic load balancing. Most of the algorithms I've talked about so far, they've been easy to load balance. Well, they've been structured enough. You can load balance them ahead of time. But many algorithms, you have to do it dynamically. And then we'll have 4 guest lectures, which are, if you like, case studies in how people have solved very large modeling problems at NERSC. All these folks are at NERSC. Climate modeling, so Michael Wehner's been in the IPCC panel for a long time. Julian Burrill, there was a headline in the New York Times about the Planck satellite collecting vast amounts of cosmic microwave background radiation about a year ago, so he's part of that project, and talk about how they look at that. And that general work has had 2 recent Nobel Prizes at Berkeley. Computational science, that's basically Facebook for molecules. So you can find your friends that you can interact with well, and so people can sort of scientists can put their molecules there, and it sort of gives you a way to say which ones are likely to have the right interaction, so I can build larger molecules with the right properties. And then what is the future of exascale computing, which will be by Kathy Yellick, who's the director of computational sciences up at LBL. So that's going to be the rest of the semester, besides, of course, working on your class projects. So, sorry I ran over. Any questions? Okay, have fun in the class projects. I look forward to continuing to talk with you about them.